Good afternoon. It's the resumption of our lecture series on Six Sigma, and the specific topic that I've chosen today to discuss with you are 2 hours long. There's like 1 hour for the first one, which is the basic idea of robust design, and the second is Taguchi Methods. How did Taguchi accomplish his robust design? Those are the two topics I'll be covering today. If you start with the first slide here, you notice this is a temple that's about almost 1,000 years old. It's in Nepal, and it's made fully of wood. Wood is the construction material for this particular temple, and it has lived through snowstorms and hailstorms and rain and everything else, and tropical sunshine and everything else. And look at the structure today. It's still standing there, and it's pretty firm, and most of the original carving can still be seen there. And it's just amazing that such a thing could last there alongside the onslaught of all these natural calamities and everything else, and particularly the harsh weather that is there in Nepal. That's an example of what we call a robust design, a design that is unaffected, whose performance is unaffected by the environmental factors. It is basically not at all sensitive to the vagaries of the environmental factor. How did we achieve this, and what are some of the insights that we have along the way, and what can the quality engineer do? This is like one of the key missions in a mission such as Six Sigma. What does he do? How does he achieve robust design in an experimental situation? How does he do that? Let me start with this little example that is of a design that is being sought for chocolate bars. Now, as you know, with global trade, our business has really expanded, and the barriers have come down, and you can buy chocolates made in Switzerland, in Asia. You can buy Japanese food products on the shelves in Malaysia, and so on and so forth. It's all pretty easy, and it's not very difficult to find apples from Europe being sold in India, for example. That's all quite common. Now, with this happening, naturally there was this anxiety on the part of merchandisers, these salespeople. They wanted to market some Swiss products, and in particular Swiss cheese and also Swiss chocolate in Asia. Now, if you live in Singapore, if you live in Kuala Lumpur, if you live in Bombay, or if you live in Madras, for example, Chennai, it's very easy for the design that is quite all right, a product design that is quite all right in Europe, not to be so successful under the conditions in which the tropics are, because particularly a couple of things are quite different between Asia and Europe, one of which is humidity, the other is heat. It's not unusual to find temperatures in for example, parts of India when it will be 45 degrees Celsius or 115 degrees Fahrenheit. That's not very uncommon. In the middle of summer, you might find temperatures like that. Now, going back to the story of chocolates, some Asian company wanted to basically market Swiss quality chocolate bars in Bombay. And one of the things they tried was they imported some chocolate bars from Switzerland, and they tried to sell them. Obviously, those chocolate bars, they were a big hit with kids, because kids always love chocolates. But the problem was that these bars, they had high plasticity as far as temperature was concerned. So if you look at the x-axis is ambient temperature. That's like the condition that's in the environment. And if I have a chocolate bar that's got this kind of plasticity, that actually means that its melting point is highly sensitive, or its stiffness is highly sensitive to temperature. What would happen is, in winter time, it would turn out to be pretty stiff. It would be pretty difficult to bite into. But in summer, it will all melt and become like a blob. It will become a blob of chocolate. Now, obviously, the kids didn't mind, except their mother started complaining. They said, well, look, when my child comes home, the hands are dirty. And of course, when he sticks one in his pocket, the shirt also gets dirty, and so on and so forth. So we really don't feel that these are good chocolate bars. They should not be probably sold here. So there was this big, huge problem when someone just blindly tried to sell chocolate bars that were really fabricated. They're manufactured, and they're quite successful in Europe. They tried to sell the same chocolate bars in Asian countries. It turned out that this was really not a robust design. Contrast that to this chocolate bar. Notice this one has got robust performance, which actually says that its plasticity, which is around here somewhere, it does not really change much with temperature. As ambient temperature is changing from low to high, which could be probably from 0 Celsius to something like pretty close to 45 or 50 Celsius here. There is not that much change in the plasticity of this chocolate bar. This one, it's got a different recipe. The difference between this chocolate bar and this chocolate bar is the difference in recipe. And this is exactly what causes the change in the properties of the chocolate bar. And the green one turns out to be a robust chocolate bar. Now, couple of things to remember here. One is, of course, we have to find the right setting for the plasticity for this. So we've got to find this design target. And I'm going to tell you about that as we go along into this talk. We've got to find the right plasticity for this green bar. That's like something that I can adjust. If I adjust the recipe, I can take it up or down. I have to find the right level for it. That's like one thing that we have to do. The second thing that I've got to do is, I've got to take a chocolate bar or the old recipe, that is this red recipe, and convert it into this green recipe. This is what I've got to do. Only then it will become a robust thing. Now let's see how this was approached by an engineer whose name is Genichi Taguchi. Taguchi's methods have become pretty popular, and they are basically all called Taguchi methods. And there are different approaches to try to produce robust processes and also robust products. Products that hold on to their good property even if the environment becomes hostile, even if the environment becomes kind of, not something that is like the rain and the snow and so on in Nepal, for example. That's an example of when the environment becomes hostile. How did we do this? There are a couple of goals in Taguchi methods. One is, of course, reduce the variability of response. That's one of the goals. Notice here, if you go back to the chocolate bar situation, this red bar has high variability. It's got pretty high variability in performance. That's like one of the goals of robust design. You got to make sure you reduce variability. And you got to achieve robustness. That means that thing should stay the same, that performance should stay the same. How is it to be done? Now, as we've learned through this course at various points, I brought along this idea of design of experiments. Design of experiments is a method by which you can play with multiple factors. These could be the elements of the recipe or the processing conditions that you can play with, and the result is always to try to achieve the final design that is the optimum design for your purpose. This whole thing is done in a very systematic way, and the way this planning for these trials is done under the framework of DOE, design of experiments. And we'll be looking at that again as we go into this. The genesis of DOE, how did DOE come about? Well, around World War and even before that, Europe tried to, many countries in Europe, they tried to raise their farm production. That's like one of the missions they had. And naturally, population was growing, and they wanted to make sure that the farms produced more corn, more wheat, and stuff like that. And in particular, when World War II came along, a lot of men were killed, so that there were not as many hands on the farm. And for the limited supply, with the limited supply of manpower, they still were looking for this opportunity to try to produce more out of the farms. Ronald Fisher, Sir Ronald Fisher, he was a statistician. He looked at this problem, and he came up with an approach that is called the factorial design approach. Here, he allowed the experimenter to manipulate multiple factors together. And also he provided a data analysis method. So when he conducted the experiment, you'd produce some data. He also gave us a data analysis method. And that analysis method is called ANOVA. This is like one of the contributions, one of the very important contributions that Ronald Fisher made. This led, first of all, raised output of agriculture. That's like one of the things that the Europeans were able to enjoy because of this, in particular in UK. The second thing that also Fisher did was he made sure that people did not conduct what we call one factor at a time experiments. And I've talked about this before. So you recall, if I do one factor at a time experiments, when another factor is changed, there may be an interaction between the first factor and the second factor. And this is always something, this is something that we are just curious about, and many times this can be destructive, the interaction can be destructive. So you may not get good performance if you conduct your experiments only by varying one factor at a time, and then you try to add things up. Things don't always go that way. That was one of the things that Ronald Fisher tried to get away from. One of these stalwarts who also worked in this area of design of experiments was George Box. He worked at the University of Wisconsin, and he, not only himself but also many of his students, they actually led to a lot of contributions, a lot of very important contributions in this general area of design of experiments. They applied it to various techniques. Many were theoretical, many were practical, many were highly significant. These contributions came from George Fisher and his students. Now, what is quality engineering? Let's just try to catch a look at this. The objective of this lecture is going to be, we will try to see what two-level factorial designs can do for us. In fact, what we are really trying to do is, what do we gain by going to a multi-factor experiment as opposed to a single-factor experiment? That's something that we'll try to understand. Couple of things that we'll try to understand, one of which is, of course, we've got to uncover the significant variables. We've got to make sure we understand, by doing the experiment, we understand which of the different factors are really active. They have the largest impact on the output. That's something that we'd like to know. The second thing we'd also like to know is, are there interactions between the effects of these different factors? This is something we'd like to be able to do. If you compare that to SPC, statistical process control, statistical process control does not really get into evaluating the effects of various factors. Statistical process control basically is a method by which we can detect shifts in the process. What we are really looking for is, we are looking for process improvement, and that can be done in a big way adopting the methods of quality engineering, and the core of quality engineering basically comprises this technique of design of experiments, or DOE. That's what we are going to be looking at. What are some of the typical applications of quality engineering? In manufacturing, we can apply this to try to improve performance of a manufacturing process. That is something we can do quite easily. When we have a process, we can improve yields, we can reduce variability, we can reduce defects, and also we can reduce cost. In design, we can evaluate many different alternatives. That's also something that we can do quite easily if we're using this approach of quality engineering. And of course, the most, shall I say, talked about method in quality engineering are the Taguchi methods. And the key tool for doing these various things, various steps in quality engineering, is DOE, design of experiments. That's what we'll be looking at as we go into this topic here. Let's take a look at what Taguchi methods really are. And of course, this gentleman is making some chocolate cakes. And let's see how does one go about producing good recipe for chocolate cakes. One very important person, this is Dr. CR Rao. He is in Pennsylvania right now. He's in Pittsburgh. And he is also one of the powerful people, a very highly knowledgeable person in the area of design of experiments, and statistics in general. In fact, it turned out that this gentleman, Genichi Taguchi, he studied under CR Rao at the Indian Statistical Institute in Calcutta, and he picked up the methods of design of experiments from Dr. CR Rao. Dr. Rao is obviously highly accomplished. He has written about 15, 16 books, and he's got over 300 papers, journal papers, and that's like a very high level of achievement that he's made. His contributions are recognized the world over. Taguchi was one of his students. Taguchi came to study design of experiments and analysis of variance and so on under Professor Rao. Taguchi was an engineer, and his interest was actually to try to influence industry practices. In particular, when the process appeared to be complex, Taguchi tried to approach this in his own way, applying the principles of DOE, but he wanted to keep his life simple, and he also wanted to keep the experimenter's life simple. And we'll see that as we go along. Taguchi also made some other contributions. Taguchi basically opened a new chapter, altogether a new chapter in the perception of quality, in the expression of quality, in the measurement of quality. This is where he took us a lot closer to the customer than had been done before. So that's like something that Taguchi also achieved. Let's see how he moved into this. What are some of his contributions? First of all, he gave us a new philosophy. He gave us something that is called the loss functions. He also emphasized the idea of targets. And I'm going to be illustrating these things as we go into this the discussion of Taguchi methods. So these are a couple of things that Taguchi gave. Also, Taguchi gave us a methodology. He gave us something that comprises 3 steps in trying to design a new product, for example. There's the system design step, then there's the parameter design step, which is the robust design step. Then you've got tolerance design. These are 3 steps that are required if you want to achieve good performance in the final product. Also, Taguchi made a contribution in popularizing a simple way to conduct multi-factor experiments, and these are called orthogonal experiments, and they are based on something called orthogonal arrays. And last of all, for data analysis also, being an electronics engineer, being an electrical engineer, Taguchi was very fond of signal-to-noise ratios. And his own way, he tried to bring that also into his data analysis. So that's also another contribution that Taguchi made. So he gave us targets, he gave us loss functions, he gave us the method of system design, parameter design, and tolerance design. Then he gave us the use, he highlighted the use of orthogonal arrays, that is something like the factorial experiment, but it is a lot simpler. Then, of course, Taguchi also highlighted the use of the utility of signal-to-noise ratio. Let's go back a little bit into the framework of design of experiments. You recognize the matrix which is to the right. This matrix is actually, it came from that golf game example that we gave. There was some teams that were playing golf and they wanted to find the effect of balls. They wanted to find the effect of drivers. They wanted to find the effect, for example, of beverage. And they wanted to sort of see what would be the correct choice for the driver, for example, or for balls, or, for example, the beverage that people are drinking. They wanted to sort of see, can we come up with the optimum choice for the driver with which you hit the ball, the drink that you take while you're playing your the game of golf, and also the ball that you choose to play the game. Now notice here, I'm using a matrix, and the same matrix has been represented here in the DOE terminology, in the DOE system. There are 8 experiments to be run. There are 3 factors involved. Each factor has 2 settings, low and high. Notice here, low and high. And I've just marked it here with minus and plus, minus and plus. Notice here there is a certain pattern that the settings of D follows as I go from trial 1 to trial 8. These settings for factor B also changes likewise from minus to plus plus, and then again minus to plus plus. And the selection of ball that goes from minus to plus plus. What is exactly happening here? Well, the first experiment will be run, or the first game of golf will be played with the driver that is the regular driver, with a beverage that is your beer, and with a ball that is the three-piece ball. That will be my first game. In the second round that I play, driver will be changed to oversized. So I've got oversized driver, the rest stay the same, and I play the game again. On this side, I've got responses, which is like the average response. Average response if I repeat the game 5 times, perhaps 10 times. It all depends how much money I have to pay to the golf course. I play those rounds and I work out my average. I calculate my average, and those averages are shown here. Those averages are also shown here for the different settings in this matrix. This matrix also is showing the same thing. And the settings, the factor settings are shown in this matrix here. Notice the factor here B, the factor D, and the factor O. Those are shown here. Now, conventionally we've been using design of experiments, which is like this study here. Conventionally, we've been using them to study average response. This is something that Taguchi found was not enough to produce good designs. Yes, you could probably find, if I wanted to maximize yield, or if I wanted to minimize defect, I could probably use a design like the conventional DOE design. Not much of a problem there. But if I wanted to achieve what we call a robust design, I'd have to do something more. I have to look at really the variability at each of these settings. I have to look at the variability of response at each of these settings, and that is really the focus of what we call quality engineering. So the conventional design of experiments, these runs would try to basically focus on the average response and determine factor effects based on that. What quality engineering does, it looks at the variability of that response as the response. So the response here is not just the average score that I have when I play golf, but also the variability that I have at each of these settings. So 61 might be the average, but the individual scores might have been 57, and then 65, then maybe 58, 62, and so on and so forth. So I have basically multiple responses. Is the variability of that, that's also of my concern when I'm looking at this problem as a quality engineering problem. What are Taguchi's key contributions? These are very important. If you look at the first contribution that Taguchi made, he gave us a new philosophy. He did give us other things also, but let's just take a look at the philosophy that Taguchi gave. Here's a plot, and notice here on the x-axis I've got some quality characteristic. It could be, for example, the size of my shirt. It could be my shirt size. That could be the quality characteristic as far as this shirt is concerned. That is what I plotted on the x-axis. Now, as far as I'm concerned, I have a unique neck size, and therefore, to be satisfied to the maximum extent, I must get a shirt that fits exactly my neck. So I really, when I put the button on, I get exactly the fit that I want. So now if that is 42, if that is 42 centimeters, my target setting then is 42 centimeters. And that's the shirt that's going to give me maximum satisfaction as far as neck fitting is concerned. If it goes away from there, suppose I buy a shirt that is size 44 or 46, my losses are going to increase. What kind of losses are these? Well, for one thing, I may have to basically take it back to the store. That's additional transportation cost. Or I may have to take it to a tailor and ask him to adjust the thing. That's something I'll also have to do. And perhaps I may not be able to do that if the shirt is too tight. So I'll have probably a loss there also as I go away from the target. Now, what has been the conventional view of quality perception? The conventional view has been, it does not really matter what product you're looking at. We've always gotten away by giving a specification. That's become our language. When I try to convey something, I try to convey my requirements. All I've done is I've given it perhaps the nominal value. I don't even call it the target value. I just call it the nominal value plus minus some tolerance. That's all I've been doing when I've been trying to communicate my requirements. But what Taguchi said is this. Let's say you've set your limits at high and low. It's not true that a shirt that is of this size suddenly becomes from good to bad. That does not quite happen. It actually happens gradually. And it rises by this concept of loss. And this loss actually, Taguchi articulated that by calling it the loss function. And I'm going to show a little formula for calculating this loss function. What it really means is, any quality you're looking at, there's always a best value that the customer wants you to have. If you're not quite there, you as the user or society at large will incur a loss, because that quality was not delivered at the target, it was delivered somewhere else. So the old idea of trying to control quality by looking at whether the product is within spec or not is not good enough. We'll have to look at it really from the point of view of saying, how far is it from the target that is there? That's going to be the real measure of quality. Let's take a look at a couple of these things. The first thing, of course, is the conventional view of quality, which just says anything that is off spec suddenly becomes bad. Once I land up in the area that is like off spec, outside spec limits, things suddenly become bad. Taguchi said that is not true. The moment you deviate from the target, society is incurring a loss, and you're basically inflicting a loss on society. And that actually will take place even if you move away just a little bit from this. And the amount of that loss can be given by this loss function. So it is not true that loss is 0 if you are within specs, and loss suddenly becomes 1 or some large number when you just exceed spec, just exceed the upper spec limit, for example, or fall below the lower spec limit. That is not the way we should be perceiving quality. We should really see, is it on target or is it not on target? Let's take an example where this was really proven out in the field. As you probably know, the Japanese, they make very good TVs, and one of the companies that produces fabulous TVs is the Sony company. And in the 80s, when the Sony company was, in the business of producing what they call the Trinitron TVs, they started exporting these TVs to US and of course to Europe and so on and so forth. In the US, these TVs became very popular. In fact, I have most of my friends, they ended up buying Sony Trinitron TVs, and they in fact even recommended that if you are trying to buy a TV, please go ahead and get a Sony Trinitron TV. That's going to be good for you. Okay, that was fine. What happened was these TVs, they suddenly became very popular because they were good TVs, and they displaced a lot of American TVs from the marketplace. Now this would mean there will be fewer GE TVs, fewer Westinghouse TVs and so on and so forth. Those really, they started to lose their market share. Like the American autos, for example, they started to lose their market share as the Japanese products started to come in. And this was naturally protested by the American workers. They said this is not fair because you're taking away our job, you're taking our market and so on and so forth. Yes, we like your product, but it's going to be at a very high cost, very high social cost. So the Japanese thought about it, and one thing they thought of doing was bring in the parts and do the assembly, which will provide a lot of jobs, fair number of jobs. And let's do the assembly in the US. So Sony company, they set up a plant in San Diego. San Diego is a little town, not very far from, it's a decent town, not very far from Mexico, for example, the Mexican border. There, Sony people, they set up their factory, the TV assembly plant. They got the parts from Japan, but they did the assembly all there. And these were, of course, American workers that were doing this. And these people, these American workers, they were doing all the fine adjustment for color, contrast, brightness, and so forth. They're making those adjustments as the TV was getting assembled. So then, of course, the TVs coming out of the San Diego plant, they also started to sell, and it went fine. There was no real problem there. These TVs were selling just fine. Suddenly, there were complaints from the field. Users didn't quite like the Sony TVs that they were buying now. The Japanese kept track of which TV that the customer was using came from which place. Was it supplied by Japan, or did it come out of San Diego? What they found was that complaints came mostly from the San Diego plant TVs. The ones that were produced in San Diego, those are the ones that really led to a lot of complaints. Then they started looking at manufacturing practices. They looked at the operation very closely, how the TVs were getting assembled, because the parts were the same. So there was not much of an issue as far as the parts were concerned, TV parts. But what they found was that when the TV was being assembled in San Diego, the worker tried to make sure that it just met specifications. So if, for example, color had to be adjusted, he made sure that he twisted the knobs and the screws and so on and so forth, and brought the performance, brought the color density, for example, exactly within specs, just within specs, and that's it, and he left it there. And he did the same thing with contrast, he did the same thing with tuning and so on and so forth. All the adjustments were made just to bring that TV that had just been assembled just within spec, that's it. And then, of course, it was pushed off, and it was packed and sealed and so on and forth and sold. So most of these, in fact, all of these TVs, they were assembled to make sure that they met specs, and these were like upper and lower spec limits. The contrast was this: TVs made in Japan were not made according to this philosophy. There, what the workers tried to do was they identified, they were told what the target was, and the target was pretty clear. The target was here, and they wanted to make sure that the TVs assembled came as close to this target value as possible as they were getting assembled. So color were adjusted to be right on its own target, contrast were adjusted to be right on its own target, various tuning adjustments, those were to be made, they were also put exactly at target. So the result was this: when these TVs came out, most of the quality characteristics, they were right on target. And these led to very few complaints from customers, very few complaints. There are hardly any people who receive TVs like this, The difference was these two types of what we call in statistics, we call them population. The population of TVs produced from San Diego, they met specification, but they did not lead to as much satisfaction in the hands of the customer, in the house of the customer, as opposed to the Japanese TVs that were assembled such that they were smack on target when they're shipped. Those led to a higher level of satisfaction and fewer complaints. Now this again highlighted the fact what you really have to do is when you're doing design or when you're doing assembly, please make sure that the quality characteristics are as close to this target value as possible, which of course is determined by a process called QFD, quality function deployment. And the same thing would be done when you are trying to fix the plasticity for the chocolate bars. Remember the green chocolate bar line, the green line that goes along. I have to find that hardness or that stiffness that is okay for children, and children perhaps who are between 6 and 12. They are the ones who should really judge how stiff that chocolate bar should be. Then of course I'll get a decent chocolate bar. Taguchi focused on offline quality control. He said all this stuff, this quality engineering thing, it has got to be done not when you're doing production, not like SPC. It has got to be done before that. It's got to be done in R&D, it's got to be done in the design shop, that's where you control what he called offline quality control. That means it was not quite at the production stage yet. You did this before you got the design ready for production. That's why it would have to be done. This would lead to a lower cost to society overall. And this led to what we call the idea of robust design, a design that results in products or services that can function over a broad range of usage and environmental conditions, such as variation in temperature, such as variation in humidity, such as variation in the quality of the components that you're using to do the assembly and so on and so forth. These are factors that the designer can specify optimally when he's doing the design. If he does not do that, then of course these things can't be controlled. Once the technology transfer has taken place and the plant is doing the job of manufacturing, they can't really do R&D there. This R&D has to be done. Quality engineering really is a part of R&D, and this got to be completed before you hand over the design to the manufacturer or the manufacturing unit. Now, what is the approach? How do you really approach quality engineering? The method is as follows. The total design step, the total design process is split into 3 steps according to Taguchi. The first thing, of course, is functional design or system design. This is the step when you choose subsystems or mechanisms and so on, and you apply basic principles of physics, chemistry, and anything else, and engineering and so on and so forth, and you come up with the first system design. Your concept is there, this is the conceptual design, and you produce a few prototypes perhaps. So you've got now a functional design that is performing all right. This is your system design phase. The second phase is when you manipulate the design parameters and you come up with what we call the parameter design. This step is called parameter design. This is also called the robust design step or the quality engineering step. What we are doing here is we've selected certain parameters for each design, for each product design that we want to come up with. We've ended up with certain design parameters. Those are the requirements that we put down there. Those requirements have been put down there, and now I have the requirements. In quality engineering, I'll be manipulating those factors. I'll be manipulating those different factors, and I'll try to see, can I improve the performance? Can I make that performance robust? This is what I'll be doing in the parameter design step. And of course, once I've got my parameter set at the optimum setting, I've got to provide a tolerance for it. And that is done at the third step called tolerance design. So quality engineering or robust design, it really proceeds in these 3 steps. First, you've got system design. Then you've got parameter design or the quality engineering or the robust design phase. And the third step is tolerance design. These are the 3 steps, and you must move systematically between these. How do we really do this parameter design? Let's try to see how we achieve a robust design, how we end up doing this. What we are really trying to do here is something that we got to go after as robustness. Robustness is something that we got to go after. And what really disturbs this robustness? It's actually the environmental factors. The design parameters that have been picked for any product that you have, those have been fixed pretty well, and they are in your control. You can set them the way you want. But unfortunately, when the product is actually used, it's being subjected to the impact of the various environmental factors. What I have to make sure is, for example, if it's just this pen, if the choice of the fluid, if the choice of the ink or the solvent is not good, then in a dry room, this pen is going to dry up very quickly. As opposed to another choice of a solvent, which is going to last longer. So that means the parts, the components of this thing that are that are easy to vaporize, that have high vapor pressure, those should not be there in a pen. If they are there, it's going to dry up very quickly. So it's not going to be a robust design. If I got to use it in the sun, for example, it really will not be something that's going to be of much use if it's not a robust design. The same thing goes if I'm trying to write upside down. If it can suck the ink as I'm using the pen, if we can suck the ink up there to the tip without too much trouble, then there is no problem there. But it's very possible that the fluid is not able to come up to that point because the position is now upside down. That's also going to be an example of a poor design. A robust design will make sure that the flow is there throughout. So there are various examples that you can come up with. That is there. What we are looking for is not only we are looking at mean performance or the average performance, we are also trying to look at what we call the variance. And this variance is caused by the impact of the, this is the variance in your response or the actual performance, and this can be impacted by environmental factor. The goal of robust design is to try to make sure that the design is insensitive, basically, to the impact of this noise. If you look at a system, you have what we call design parameters. We've got certain target settings that we have to set. Then you've got these noise factors. Then you've got the actual performance. What we have to really do is, in robust design, we got to identify the product process design that have little influence on performance or significant influence on performance. So the first thing I have to do is, of the various design factors, I have to find those factors that have an impact on performance. This is something I've got to separate out. And DOE is a great way to do this. DOE is a great way to try to manipulate these different five or six different factors and find the ones, 2 or 3, that are really the significant ones. This isolation is very important. This separation is very important. This identification is very important. This is done as step number 1 in robust design. Then, of course, we got to make sure we minimize the variation in the output. We do something by which the design becomes less and less sensitive to the environmental factors, to the impact of environmental factors. The third thing, of course, we should try to do is we should try to minimize processing costs. That's also something we should be able to do. The method used for this is DOE, design of experiments. And there are many examples. I've given some examples. Chocolate mix, then the tile company trying to produce float tiles, and Sony TVs, and there are many other examples of robust design. Let's try to get a little deeper into this. There are certain things that are called design factors. These are the ones that I'm going to change. So, for example, for a pen, if it's a writing medium, this is going to be a writing tool basically. It's going to be the choice of the tip, the quality of the ink that I'm using, the delivery system, the holding system, the protection of it, and all. These are all design parameters. I can change them. As far as robustness is concerned, like I said earlier, if this pen misbehaves in hot sun, for example, or if it dries up too quickly in a dry room, it's not a good design. It's not a robust design. Because I'm not going to be using this pen all the time, what we call ideal situations, ideal conditions. I'm not going to be doing that. I'll be using in perhaps hostile environment, but it should retain its good performance. That's going to be a robust design. If it retains its good performance, that's going to be a robust design. To do that, what we have to do is we've got to obviously identify the control factors, we've got to identify noise factors, we've got to identify the adjustment factors, and what we call signal factors. These have to be identified. And Taguchi clarified that almost every system will involve these factors. It's our job, the quality engineer, to make sure that we understand these factors. How do we basically find the right settings? And for this, Taguchi provided a method. And these methods, they utilize a special structure, a special matrix structure for the settings of these different parameters. That's something that is done by what we call use of the orthogonal arrays. I'm going to be giving you some examples of this. There are various types of experiments you can run. If you've got multiple factors to play with, there are various types of experiments you can run. You can run what we call full factorial designs, full factorial experiments, or you can run fractional factorial experiments, or you can run what we call central cuboid experiments, or we can run just the plain and simple orthogonal experiments. Now, what is the use? What is the difference between these different experiments? First of all, they are matrices. These control the number of trials you'll have in your experiments. And number of trials basically determine what you can do with the experiment, what kind of message you can get out of the experiment. So full factorial experiments, basically they tell you a lot. They will tell you about not only about main effects but also about interaction effects. All those things can be found by full factorial experiments. If you're looking at central cuboid design, for example, in some cases we want to really generate the response surface. We want to come up with a mathematical formula for the response surface. For this, what we have to do is we have to use some other points in space aside from what the full factorial design is doing. So I've got the full factorial plan. I collect some additional data at some other points which are specified by the central cuboid design. And that design is going to help us guide and find the parameters for the regression model, which will be for the response surface. That I can then go ahead and apply some other technique, some other optimization technique, and I can optimize the process or yield or something like that. Then there are partial factorial designs, which means I do not really run all the trials of the full factorial design. Instead, I drop some, and I drop them very sensibly. I do not drop willy-nilly, because it all depends on the purpose for which I'm running the experiment. If I'm interested in only knowing main effects, that means single factor effects, I will be probably dropping some of the interaction capabilities, and for that I can drop some of the trials, and that I can do. And one extreme situation is the orthogonal array, when I can only find main effect and nothing more than main effect. And these are the ones that still can tell us a lot about the behavior of the system. And these are the ones that were basically exploited by Taguchi. Taguchi exploited orthogonal experiment, and we'll be taking a look at those. Let's take an example. Suppose I have an experiment, suppose I have a process, and I've got a simple fishbone diagram that will recognize here. And it's got three factors here, A, B, and C. And I'm basically very curious about the response of the system. Or I really want to know, is A important as far as response is concerned? Is B important as far as response is concerned? Is C important as far as response is concerned? That means, does A have an impact on response? Does B have an impact? Does C have an impact? These are the three questions I have. I may also have an inquiry about any interaction that is possible between A and B. Do these factors A and B, do they have an interaction? Do their effects interact with each other, or do they act in a sense what we call independently or additively? Is there an interaction between A and C, and is there an interaction between B and C? And is there such a thing as A, B, C three-level interaction? Are these things present in the system? Many times when the system is given to you, you do not really have an equation that will tell you about these dependencies. Like, for example, if I look at this curve here, I look at response as the function of what we call A, B, and C. Now, this could be the effect of factors A, B. So I could just have factor effects A, B, and C. I could also have interactions. AB interaction, or BC interaction, or AC interaction, and also perhaps a third order interaction ABC. These things, these are the ones that make life complicated. These are easy to evaluate, and if I just have to focus on these, I could use what we call an orthogonal array. But if I also have to find, in addition to this, if I also have to find these, I have to use what we call a full factorial experiment. Full factorial experiment. So I could run these experiments. I could run basically orthogonal array experiments, or I may have to run full factorial experiment. It all depends on the purpose of the experiment. The reason I want to study this thing. If this is to be done empirically, I'll have to run a matrix experiment, and I'm showing a matrix. If you come to this table here, I'm showing a matrix. These are trial number 1, 2, 3, 4, 5, 6, 7, 8. And look at the factors, factor A, B, and C. And these are the settings now. These are the settings now of the different levels I'm going to be First, I'm going to be a very simple experiment. I'll put A at 2 levels, B at 2 levels, and C at 2 levels. So for A, I've got 1, 2, 1, 2, and so on. So notice these are changing as I go from trial 1 to trial 2 to trial 3 and so on and so forth. These settings are changing 1 and then 2, then 1 and 2 and so on and so forth. For B, I also have got 2 settings there, 1, 1, 2, 2, 1, 1, 2, 2. And for C also I've got 1, 1, 1, 1 and 2, 2, 2, 2. When I combine the settings of A, B and C the way it's been done here, the remaining columns, they easily allow me to calculate these interaction effects. For example, the AB interaction effect can be found by taking tips from this column. AC interaction can be found by taking tips from this column. BC can be found from this, and ABC interaction can be found from this. What is the advantage here? I ran 8 trials. From that, I'm able to find not only the main effects of A, B, and C, I'm also able to find these 2-factor interactions and also one 3-factor interaction, which is possible. All these could be done if I would run the full factorial experiment. And such an experiment, of course, is the most powerful one. I'm running 2 cubed. That means a total of 8 experiments is what I'm running here. And that involves now 3 factors. This is like one way. Now suppose, for some reason, I suspect maybe there is not much interaction between these different factors. Then, of course, these columns that we saw earlier, these columns BC, AC, AB, and ABC, these columns would be idling because I've got nothing there. There's nothing wrong in assigning other factors that also hopefully will not have an interaction with A, B, and C. And those can be D, E, F, and G. I've now put in this matrix, I've assigned now 7 different factors when I'm studying only 8 trials, when I'm conducting only 8 trials. I'm conducting 8 different experiments, and I'm now going to be studying the effect of what we call 7 different independent factors. And such a plan is called what we call an orthogonal array plan. What is the advantage of these plans as opposed to the full factorial plan? For one thing, it lets you study many more factors. Like here, with the same 8 trials, I'm able to run 8 experiments. I'm running 8 experiments, and I'm able to study 7 factors. When it came to when we went back to the full factorial experiment, this one, there with 8 trials, I'm able to study the effect of basically A, B, and C, 3 factors only. But what we gain with the full factorial design is the effect of interactions also. This is not something that I can do with my OA. OA is this one. With this, I cannot study. In fact, it turns out that these interactions, they are now confounded with main effects. But what Taguchi found was, at least in 50% of the cases, you could get away by doing your OA experiments, and not much would be lost. We'll be taking a look at some of these things. I've got an example here. Let me show this example to you. There was a tile company, and the name of the tile company was the Ina Tile Company. They had a peculiar problem. They had a kiln. They had in Hindi we call bhatta, an oven, in which these tiles were baked, and the tiles combined a large number of factors. There will be the recipe for it. There will be china clay, there will be moisture, there will be various things, various components went into making the mix. Then, of course, there are process conditions, heat, and the amount of ventilation that was there, and so on and so forth. Those things would be there. The placement of those tiles before baking took place. All those things, these were like control factors. The problem was, this company were suffering from very poor yield. They were 20-25% of their production was actually good quality tiles. The rest they had to crush back again, and they dump it again, and make the raw tiles again, and then bake them again. So it was like a lot of rework, a lot of waste, a lot of rework. Huge muda in this particular example, huge muda. So what they tried to do was, they said, well, is there some way by which we could optimize the settings for these factors? And they identified, by brainstorming, they were able to identify 7 different factors. At that time, Taguchi heard about this problem, and he became involved, and he started to advise them. And what Taguchi did was he set up a simple orthogonal array, and I'm showing that on the screen here. The process factors are these A, B, C, D, E, F, and G. And he set up this matrix that comprised 8 trials. And for each of these process factors, he chose 2 levels. These were the extremes of the working range in which these different variables could be changed, could be altered. So the first one could be changed between A1 and A2. Second one could be changed between B1 and B2 and so on. These were distinct numbers. These were distinct settings. But they were clearly 2 settings for each factor. Having done that, Taguchi ran the trial. So the first set of trials were made under this setting. On the right hand side, I report the fraction of tiles found defective. And notice here that 16 here, 17 here, 12 here, and so on and so forth. So I have here the numbers. In couple of places, of course, they are pretty bad, as you can really see. And in other cases, they are pretty good. Now, this is the data that was then analyzed. And how was this done? We calculated the averages. And I'm going to show you 1 or 2 examples of this calculation. I'm going to be just taking a little sheet of paper here, and I'll use my calculator. I'm going to be working out, for example, for A1, we are going to be finding this percent defective. Let's do that. All I have to do for that is I have to basically add up the settings under which runs have been made with A set at A1. A set at A1. What are the readings? Readings are 16 plus 17 plus 12 plus 6 divided by 4. And let's do that. Let's do the number there. We have 16 plus 17 plus 12 plus 6. We do the total and we divide that by 4. 12.75. Let's take a look. The first reading is 12.75. Similarly, I could do A2, I could do B1, I could do B2, and so on and so forth. So, in fact, these are the averages. This is the average percent defective found when factor A was set at A1 and factor A was set at A2, and I got this reading. Similarly, for B, when B was set at B1, I would get this reading. When B was set at B2, I would get this reading, and so on and so forth. If you see this way, the way this matrix is organized, there's a property of it, and that is called the orthogonal property, because of which I'm able to separate out the effect of A, factor B, factor C, factor D, and so on. I'm able to do that. When I do that, I can show the results graphically. This is, of course, a numerical display of the thing. When I show it graphically, I can now show you the effect of A. When A changes from A1 to A2, percent of defects go up. When B is changed from B1 to B2, percent of defects come down. Similarly, percent of defects come down here, they go up here, they come down here, they go up here, and so on and so forth. Now, if the goal is to reduce defects, I should not be using these settings. I should instead be using these settings here. So my optimum setting here is going to be, if I write down the optimum setting, again going back to my set there, optimum setting, optimum factor settings. These are going to be, for A it's going to be A1, then for B it's going to be B2, because that's going to give me a lower rate of defects. C is going to be C2, D is going to be D1, E is going to be E2, F is going to be F1, and G is going to be G2. These are my optimum settings. If I now run a process with these weightings, I should expect to see minimum defects. And that would be done in what we call a verification experiment. And this was done basically by Taguchi. This was done once the data was complete. It was done this way. This is like a great example where a simple plan was used, a simple experimental plan was used, and he has accomplished a lot. In fact, he was able to reduce the defects from a pretty high level to a pretty low level just by manipulating the factors in a way that would be guided by this OA, the orthogonal array, and he was able to do that. This is one of Taguchi's major contributions. He gave us an empirical method that turned out to be a pretty simple, straightforward method, and that's like exactly what we showed in the thing. Now, this is not a new design. This is not a new plan. Similar plans have been there before, and in fact, what Taguchi did was he just made a clever use of an existing plan that was already there. This was clearly not a full factorial design. It is a partial factorial design. It actually was partial of a part of the full factorial design that would be there. If you remember, this factor involved 7 factors. So in actual fact, even if I had 2 factors only, I would have had to run so many full factorial trials. And Taguchi didn't have to do that. Taguchi just used the 8-line orthogonal array. We'll follow this in a couple of minutes. We'll be following this. So just wait for the next hour. Thank you.